Hey, welcome to lecture 6 of linear algebra. We first talk about the diagonalization. In many cases, the eigenvalue and the eigenvector information contained in a matrix A can be displayed in the famous and also very useful factorization of the form A equals to P, D, P inverse, where our D is a diagonal matrix while our P is invertible. And we will see that the factorization enables us to compute a to the power k very quickly, even for k very large. So this is the fundamental idea in many applications of the linear algebra. So let us start with an example. So if our diagonal matrix D is of the form 5, 0, and 0, 3, then we have D squared equals to 5, 0, 0, 3 times 5, 0, 0, 3. So this equals to 25 and 9. And if we are going to multiply D to the third, it equals to D times D to the power of 2, which is 5003 times 25009. So that gives us 5 to the third power and 3 to 3. So similarly, we can see that for d to the k, it equals d times to d to the k minus 1. And following this order, we know that it is just 5 to the k, 0, and 0, 3 to the k, and know that k is greater or equals to 1. So for our A equals to P, D, P inverse for some invertible P and diagonal matrix D, our AK is also, since it can be factorized into this form, so the computation of it could be eased by doing so. So let us see an example, see an exercise. So if our A is 7, 2, minus 4, and 1, we want to find the formula for A to the K by A equals to P D P inverse, where P is invertible and D is the diagonal matrix given by P equals to 1, 1, minus 1, minus 2, and D equals to 5, 0, and 0, 3. So the standard formula for the inverse of a 2x2 matrix P inverse. So we first find the P inverse. So since we know that by the Gaussian elimination, we know that so we cancel this guy first. So we add the first row into the second row. So that gives us a 0 and minus 1, followed by 1 and 1. And then we add the second row to the first row, and this gives us a so this gives us a 1, 0, 0, minus 1. So that is 2, 1, 1, 1. And lastly, we need to make this into the standard form. So we multiply the second row by minus 1, so that gives us 0, 1, 2, 1, minus 1, minus 1. So we know the inverse of P equals to 2, 1, minus 1, minus 1. Okay, so Next, by the associativity of the matrix multiplication, we know that a to the second, since we know a could be factorized into P inverse, so a to the second is equivalent to this. And so what we have is P times D times P inverse times P times D times P inverse. And since this is the identity, so this equals to PD squared P inverse. So since we know P and P inverse, it left us to calculate D inverse. And since D is 5003, so its second power is only 5 to the second 0 and 0, 3 to the second. So this gives us PD to P inverse equals to, so first is P, 1, 1, minus 1, minus 2. I'm running out of space, so PD P inverse equals to this guy times D squared, and then times P inverse, which is given by 2, 1, minus 1, minus 1. And similarly, we know that A3 equals to PD P inverse times A squared. So that is PD P inverse times PD second P inverse. So we have, I'm sorry for that. So we have P D P inverse times P1 so we have D3 P inverse. So similarly, we can generalize this into the power of k. So we know that AK equals to P dk P inverse. So that is just 1, 1, minus 1, minus 2 times 5 to the k and 3 to the k, and then times 2, 1, minus 1, minus 1. So we can uh, make it to one matrix, so that is 2 times 5 to the k minus 3 to the k, and 5 to the k minus 3 to the k. We have 2 times 3 to the k minus 2 times 5 to the k, and 2 times 3 to the k minus 5 to the k. And we're done. And since this diagonalization is so important and so powerful, we want to know under what condition a matrix or a square matrix is diagonalizable. So we first offer the definition. We say that a square matrix A is said to be diagonalizable if A is similar to a diagonal matrix. So that is A equals to PDP inverse for P invertible and D diagonal matrix. So yes, in fact, this definition offers no insights for under what condition it really is diagonalizable, since we know under this form it's more a calculation matter. So now we offer a theorem which gives the characterization of diagonalizable matrices and tell us a suitable construction for the factorization, and this is called the diagonalization theorem. So we say that an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So in fact, A equals to PD P inverse, with D is a diagonal matrix and P is invertible if and only if the columns of P are n-linearly independent eigenvectors of A. And in this case, the diagonal entries of A are obviously the eigenvalues. So in this case, the entries of the diagonal matrix D are eigenvalues of A that correspond to the columns of P or respectively to the eigenvectors of P. So this is why the eigenvector information is contained within a matrix, and it could be displayed by our factorization, and this is why this is so important. And also, there are some remarks. So first, let us clear the possible confusion. So that is a diagonalizable matrix needs not to be non-singular. And secondly, A is diagonalizable if and only if there are enough eigenvectors to form a basis of Rn. So exists enough eigenvectors, namely V1 up to Vn, such that it forms a basis for Rn. Or perhaps we have more than n items. But since we want linearly independent ones, so let us just write in this form. And we shall call this basis an eigenvector basis of Rn. So yes, the relationship between the column space and the eigenvector space could be somewhat confusing. And now we use a very elegant interpretation to tell the difference. So let us use another remark to tell this difference. So if we are going to regard our matrix as a linear operator, so that is T of V equals to AV for V some vector, and T is the linear transformation with A its corresponding matrix. So the column space, so what is the column space? We know that it is the range of the linear operator. So that is the column space of A is just the range of T. And the eigenvectors for non-zero eigenvalues will be members of this range. So that is, if AV equals to lambda V, then we have A times lambda inverse V equals to V. So The span of the eigenvectors with non-zero eigenvalues is contained in the column space. So, and moreover, the span of the eigenvectors with eigenvalue 0 is the null space. So let us just write this down. You know, that's firstly, the span of the eigenvectors of with non-zero eigenvalues is contained in the column space, while our span of the eigenvectors with zero eigenvalues is the null space of A. Okay, let us do an exercise. I forgot my counting stuff. That's 1. Okay, so this is 2. So we want to diagonalize A equals to 1, 3, 3, minus 3, minus 5, minus 3, and 3, 3, 1, if possible. So yes, we need to check the diagonalizability. So solution. So recall in our last theorem, we know that first, it is diagonalizable if and only if it has n linearly independent eigenvector in the eigenvectors. So first, we want to find the eigenvectors and the eigenvalues of A, and so if this step fails, we can tell nothing about the diagonalizability, so we can do nothing about this matrix for its diagonalization. But in finding the eigenvectors, we first need to find the eigenvalues. So step 1, we find the eigenvalues of A. So in finding its eigenvalues, we just use the form A minus lambda I3, which is, so 1 minus 3 is minus 2. Sorry, is lambda. So it's 1 minus lambda, 3, 3, minus 3, minus 5 minus lambda, minus 3, 3, 3, 1 minus lambda. So we use row reductions, and it uses the equation. So one can check themselves by using the row reduction, and it gives us its determinant when it's 0. So determinant of lambda I3 equals to lambda third minus 3 lambda squared plus 4. So that is actually minus lambda times, we have, sorry, so this should be minus lambda minus 1 times lambda plus 2 squared. So we have that the eigenvalues are lambda equals to 1 with multiplicity 1, and lambda equals to minus 2 with multiplicity 2. And the next step, the most important step, is to find the linearly independent eigenvectors. So linearly independent eigenvectors. So Since this is a 3 by 3 matrix, so we need 3 vectors. And this step is crucial since once we fill, it cannot be diagonalized by our previous result. Actually, it's this theorem. So now, since we know the eigenvalues, so when lambda equals to 1, so when we plug back to the original equation, we have that our v1 equals to 1 minus 1 and 1. And the basis for our lambda equals to minus 2 is that v2 equals to minus 1, 1, 0. And of course, we have v3 equals to minus 1, 0, 1, since it has multiplicity of 2. We have two eigenvectors here. And so the calculation of these 3 eigenvectors could be left as an exercise, and as well as to check that these 3 are actually linearly independent. So we skip this elementary exercise and move to the third step, which is the construction for P by our vectors. So we know P, since by the theorem, we know that the columns of P are unlinearly independent eigenvectors of A. So our P, the construction is very simple. We just plug in V1, V2, and V3, and this gives us the matrix of the form. And then the last step, which is to construct D from the corresponding eigenvalues. So in this step, it is essential that the order of the eigenvalues matches the order of the chosen columns of P. So if we use the eigenvalue, so we need to use the eigenvalue lambda minus 2 twice, one for each of the eigenvectors corresponding to lambda minus 2. So that really means we have our D, since it is diagonal matrix, we have for the first, since the first lambda equals to 1, the first eigenvalue has only multiplicity of 1, so we need to ignore that. But for the second one, lambda minus 2, it has multiplicity of 2, so we need to times the, since we want the diagonal, the main diagonal to be non-zero elements, and it has minus 2. So we need to multiply it inside twice, since it has multiplicity of 2. So one can check that P or D really work. So so to avoid computing P inverse, we can simply verify that AP equals to PD. This is equivalent to A equals to PD, P inverse, since we are assuming P is invertible. And of course, one need to check that P is indeed invertible. So that is only a calculation of the determinant. So we have that AP equals to, so A is this guy, and so let me just write down the result, and one can check by himself that we have 1, 0, minus 2, and our PD equals to the same. Minus 1, minus 2, 0, 1, 0, minus 2. And so they coincide, and so A is indeed diagonalizable, and we found the PED and the corresponding P inverse. And now we shall provide a theorem that provides a sufficient condition for a matrix to be diagonalizable. So we see that n by n matrix A is diagonalizable with n distinct eigenvalues is automatically diagonalizable. So this is efficient since we see that in this guy, in our last exercise, this A has only two distinct eigenvalues, but it is still diagonalizable. So yes, diagonalizable does not imply that it has n distinct eigenvalues. So let us use this theorem to try to do an exercise. So we want to determine the matrix given by 5 minus 8, 1, 0, 0, 7, 0, 0, minus 2 is diagonalizable. So since this matrix is triangular, its eigenvalues are just 5, 0, and minus 2. So yes, it has 3 distinct eigenvalues, so it is diagonalizable by our theorem too. And now, if an n by n matrix A has n distinct eigenvalues with corresponding eigenvectors, namely v1 up to vn, and if p equals to v1 up to vn, then p is automatically invertible since its columns are linearly independent. And when A is diagonalizable but has fewer than n distinct eigenvalues, it is still possible to form a P in a way that makes P automatically invertible. So for the case P, so for the case A is diagonalizable, but with less than n distinct eigenvalues, we use this result. So namely, A is still n by n, but so A is n by n with distinct eigenvalues being lambda 1 up to lambda p, where p is smaller than n. So when 2 is smaller equals to k, smaller equals to p, then the dimension of the eigenspace of A, for our lambda k is less than or equal to the multiplicity of the eigenvalue lambda k. So we see that in the construction of this D. And the second is that the matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspaces equals to n. This is the case if and only if both 2a and 2b are valid. So 2a is that the characteristic polynomial factors completely into linear factors. And 2b is that the dimension of the eigenspace for each lambda k equals the multiplicity of lambda k. And the third result is that if A is diagonalizable and K is a basis for its eigenspace with respect to lambda k, where lambda k is the eigenvalue for all k, then the total collection of vectors in the size given by B1 up to Bk, it in fact forms an eigenvector basis. Eigenvector basis for Rn. And now let us move to the eigenvectors and the linear transformations. So we need to understand the matrix factorization A equals to PDP inverse as a statement about linear transformations. And so that is, we want to see that x maps to ax is essentially the same as the mapping u maps to du. And a similar interpretation we apply to A and D, even D is now the diagonal matrix as we see above. So recall that a linear transformation T from Rn to Ri can be implemented by the left multiplication by a matrix called the standard matrix of T, of the linear transformation T. And now we need the same sort of representation for any linear transformation between two finite dimensional vector spaces. So that means our n and I are both finite. So now let us consider V of the dimension n and W. So dimension V is n and dimension of W is I'm, and V and W are both vector spaces. So consider there is a linear transformation preserving the vector space structure from V to W. And to associate a matrix with T, we can choose the ordered basis. So that means the basis with the partial ordering smaller equals 2 is well defined. So we have a basis for V, an ordered basis for V, namely B, and an ordered basis for W, namely C. So if we are given an X lives in V, and since this is a basis, so we know there is a coordinate vector for X in Rn. So that is X B. And we know that from Rn to V, it is a coordinate mapping, and it is an coordinate isomorphism. And also, same thing happened for since x lives in TV, so we have Tx lives in W, so we can denote on the other side Tx on C. So obviously this guy lives in Rn, while this guy lives in Rn. And the connection between these two guys could be easily constructed. So namely, if we consider B1 up to Bn defines our B. So if we are we are given that x lives in V, and R1 up to Rn lives in the underlying number field being the scalars, we have that x has the unique representation by R1 B1 plus all the way down to Rn Bn, and we can denote our x with the coordinate basis B equals to given our R1 up to Rn. And since our T is a linear transformation, so we have T of x equals to, since our linear transformation preserves scalar multiplication and vector addition, so we have R1 T of B1 plus all the way down to Rn T of Bn. So that is our coordinate basis for this guy is just T of T of B. That is R1 T of B1 to C plus all the way down to Rn T of Bn C. And since these C coordinate vectors are in Rm, so this equation can be rewritten in the matrix equation. So that really means for our T x C, it's actually equals to I'm times x with coordinate basis B, where our I'm is a matrix with TB1, C, TB2, C, and all the way down to our TBN, C. So this matrix I'm is a matrix representation of our linear transformation T, and it is called the matrix for T relative to our bases B and C respectively. And moreover, this equation shows, guys, as coordinate vectors are concerned, the action T on X may be viewed as a left multiplication by the corresponding matrix I'm. So let us do an exercise. So suppose our basis B has B1 and B2 as its elements, and is a basis for V, and C has C1, C2, and C3, which is a basis for W. And we know that T from V to W is a linear transformation with our T of B1 equals to 3C1 minus 2C2 plus 5C3 while our T of B2 equals to 4C1 plus 7C2 minus C3. And we want to find the corresponding matrix for the linear transformation T relative to the bases B and C. So namely, we want to find I'm, and this is the solution. So firstly, the C coordinate vectors of the images of B1 and B2 are namely T of B1 with coordinate basis C equals to 3 minus 2 and 5, while T of B2 C equals to 4, 7, and minus 1. So as we see above, M is just uh, 3 minus 2, 5 with 4, 7, and minus 1. We're done. So if B and C are bases for the same space V, and if T is the identity transformation, so namely V equals to W in this case, and T is the identity transformation, that is T of X equals to X for X lives in V. Then this matrix M is just the change of coordinate matrix. So the B matrix for T, so the B matrix for our T from V to V is really T of X on B equals to T on B times X on B. This holds for all X in V. And in applied problem involving our Rn, a linear transformation T usually appears first as a linear transformation, namely X maps to AX. And if A is diagonalizable, then there exists a basis B for our Rn consisting of the eigenvectors of A. And now we will state a theorem which shows that if this is the case, then the B matrix for T is diagonal, and diagonalizing A amounts to finding a diagonal matrix representation X maps to AX. So this is our theorem, which is called diagonal matrix theorem. And before that, I want to so for the audience who are already familiar with some functional analysis, for some linear transformation, we have the property for some norm to behave like this. And this is the very starting point for defining. So, okay, so let's go back to our diagonal matrix theorem. So suppose our A equals to P dP inverse, where D is the diagonal n by n matrix and P is invertible. And if B is the basis for Rn formed from the columns of P, then D is the B matrix for our transformation X maps to AX. Now we shall move to the last part of this lecture, which is complex eigenvalues. As we see in the last lecture, since for the characteristic equation for matrices, we know that it could happen that there appears some complex eigenvalue. And for a real matrix A which has some complex roots, these roots provide critical information about A. So the key is to let A act on the space Cn. So yes, we are changing our underlying number field. So first definition about the complex eigenvalue and the complex eigenvector, and if there is no confusion, we will just know them as eigenvalue and eigenvectors correspondingly, since they are the solutions or the roots to the characteristic equation. So actually the polynomial. Okay, so a complex scalar named lambda lives in C satisfies the equation a minus lambda I n for a in unbounded matrix is zero if and only if there exists a non-zero vector x in Cn such that ax equals to lambda x. And this lambda is the complex eigenvalue and the corresponding x is called a complex eigenvector. So let us do an exercise. So if our A equals to 0, minus 1, and 1, 0, then the linear transformation x maps to ax on our R2. It rotates the plane counterclockwise through a quarter turn. And so that is from this part, we are moving to this part, and we can see after 4 moves, it just goes back to where we start. So this A is periodic, and obviously, no non-zero no non-zero vector is mapped into a model of itself. So A has no eigenvectors in R2, hence it has no real eigenvalues. In fact, we can check by the equation, namely, we have A minus lambda I2, which is minus lambda minus 1, 1, minus lambda. So we have the determinant being lambda squared plus 1. And we want this guy to be 0. So of course, our roots are positive and minus I. So we are considering our A unreal, but if we permit our A to act on our C2, we have 0 minus 1, 1, 0 times our 1 minus I equals to I1 equals to I times 1, and this is minus I. And on the other hand, we have 0 minus 1, 1, 0 times this case 1 and 1 and I, which is just minus I and 1. So it is minus I times 1 and I. So I and minus I are eigenvalues, and these guys are these guys are the corresponding eigenvectors. And if we let A be an n by n matrix, with its entries being real, then we have that AX conjugate equals to A conjugate X conjugate equals to AX conjugate. This is together. And this shows that so when lambda is an eigenvalue of A and X is the corresponding eigenvector in Cn, then we have that so AX conjugate equals to AX scalar conjugate equals to, since lambda is the eigenvalue and X is the corresponding eigenvector in Cn, so we have lambda X conjugate equals to lambda conjugate x conjugate. So we know that, so starting with a lambda being an eigenvalue of A, we know that lambda bar is also an eigenvalue of A. And we know that start with x being an eigenvector of A, and we end up with x bar being the another eigenvector, and it is corresponding to lambda bar. And this shows that when A is real, its complex eigenvalues occur in conjugate pairs. So this is important. When A is real, its complex eigenvalues occur in conjugate pairs. And now we state a result to end our lecture. So that is, if we let A be a real 2x2 matrix with a complex eigenvalue, namely lambda equals to A minus Bi, where our B is non-zero. And so with an associated eigenvector, namely V lives in C2, then we have that A equals to P C P inverse, where our P equals to real part of V and the imaginary part of V, and our C equals to A, B, minus B, and BA. This is a very powerful result. And this concludes our lecture, today's lecture. And in the next lecture, that is lecture 7, we are going to go through the introduction about the quadratic forms. Okay, so thank you for watching, and see you in the next lecture.